our next speaker is P Hammami, as I said. She is epidemiologist and modeler at the French Agency for Food, Environmental and Occupational Health and Safety. I hope I said it, the title completely. And so you will talk about epidemiological implications of network structure. So please, the floor is yours.
Thank you. Good morning. So thank you to you all to be there today. So I'm going to present you, as you said, the modeling approach that we developed to study the epidemiological implication of network structures in the spread of hepatitis E virus within the French pig industry. This study was a collaboration between two French institutes, ANSES and CIRAD, and Stefan Wilgren, that you all know, I think, from the National Veterinary Institute of Sweden. It was funded by a One Health European joint program called BioPiggy. So hepatitis E, it is an infectious zoonotic disease that can be transmitted to humans in various ways, including the consumption of undercooked pigs. In industrialized countries, human cases used to be sporadic, but it increased over the last decades and became a cause for public health concerns. So in those countries, the major transmission route that was identified was, in fact, the meat consumption. Therefore, our study aimed at targeting the most efficient biosecurity strategies for the swine industry to reduce HEV foodborne contamination at national scale. So as the disease is asymptomatic in pigs and no mandatory regulation have been put in place, the virus has been circulating silently and is now widespread in many European farms without any impact on the production because it's asymptomatic. It is really challenging to convince farmers to implement any specific measures. So that's why it's essential to assess the impact of biosecurity in order to focus the communication on the most effective measure and to limit the risk of introducing infected pigs in the food chain. In the frame of Farm to the Fork project, the BioPiggy project, we developed an approach to simulate HEV spread among domestic pigs at national scale. HEV transmission between pigs occurs through fecal-oral routes, either by direct contact with an infectious pig or by ingestion of virus in the contaminated environment. Therefore, the study we did follows three successive objectives. The first one was to simulate the domestic pig spatial distribution and the population dynamics at a scale that would allow to discriminate direct and environmental transmission, as well as including the between farm movements, because we know that it is the major driver of HEV spread between farms. The second objective was to simulate disease spread, including local epidemiological parameters, to test the impact of various biosecurity measures. And finally, it was to use this global approach, this model, to provide epidemiological recommendation at national scale. So to understand how we developed the demographic model, I will give a brief reminder about the swine production cycle. So over the production chain, groups of pigs called batches are reared together from birth to slaughter. So batch of sows are inseminated in a gestation unit. They will be moved in a farrowing unit where they will farrow, and the piglet will be weaned there before being sent to a post-weaning unit called nursery. And finally, they will be heading to a fattening unit, final step before slaughter. So the duration of stay in each one of those sectors can change and is depending on the batch rearing system. So it will be always the same in a given farm, but can be different between farms. Each unit is composed of one to multiple rooms, and each room is divided into multiple adjacent pens where animals are gathered. The number of rooms is depending on the batch rearing system also. Within farm, HEV transmission between pigs occur within a pen through fecal-oral route or through the environment between the adjacent pens. Nevertheless, as we saw during their growth, animals are moved from one production unit to another. So those movements can happen either within a farm, but also between farms. Indeed, each farm can be composed of 1 to 4 of those units, depending on the main husbandry activity. So here you can see how animals can be transported from one farm to another. For example, here in red, it's a movement that can be done for the sows, sent from breeding units to producing units, the piglets, the growing pigs, and finally the barrows that are sent to slaughter. Because of their potential to move infected animals, those movements are known as the main factor of spread between farms. Therefore, we simulated the pig population dynamics at national scale as a metapopulation, considering the pens as subpopulation aggregated into room, and then unit, and then farms. So to simulate the within farm movement, we extended a previously developed metapopulation model that has been described in this paper. To improve the flexibility of this model, the within farm dynamics was driven by parameters defined at farms level. So we increased the flexibility by increasing the type of farms, the batching system, and adding higher variability into sizes. So each farm is defined by its structure, the husbandry calendar, and the batching system. So information on more than 28,000 farms were collected by the French National Pig Identification Database, BDPOR, and analyzed to feed the demographic model. Then the within farm movements were, even if the within farm movements were prioritized, when it's impossible, for example, if a post winner wants to send the growing pigs, there is no finishing or fattening unit. So when the animals have to go outside, the choice of the destination was stochastic and based on probabilities of contact. The initial model that was previously developed used empirical probability based on observed movements. So to improve the predictive capacities of the model, we attempt to identify the drivers of the movements, and thus to be able to estimate between farm movement probability for all pairs of farms and not only farms that were in contact in the past. To do so, we used what we call an exponential random graph model. These types of models are modified logistic regression, aiming to explain a given network based on its topology and the characteristics of the nodes and the links. So for a given network, we attempt to explain between farm movements by the number of links, so structural factors, the distance between farm, and various farm characteristics such as the type, the company, the size, the presence of an outdoor rearing system, the batch rearing system, and the location either on the mainland or on the island Corsica. Following a classical bidirectional stepwise procedure, we successively adding and removing the covariables and comparing the Akaike criterions, we selected key parameters of the models and estimated the probability of animal movement between all pairs of farms. So 4 years of movement were collected by the same French database between 2017 and 2020. And as we assumed that sows, piglets, and growing pigs movements were submitted to different drivers, we divided the global network into 3 subnetworks that were analyzed independently from each other. As you can see on the left, the maps of the movement of the second semester of 2019 for the sows, the piglets, and the growing pigs. On the right, it's the network statistic that we calculated for monthly on the left of each plot, semestrial and annual networks. Without going into details, this first exploratory analysis with the network statistics supported the structural stability of the network over time, despite a variation in contact between farms. What I want to say is that for a given network, even if it's composed of different movements for a given period, Even if the network is composed of different movements, the network will present the same structure and global property than another period, for example, another semester. This is supporting the hypothesis of an absence of seasonality. So no need for temporal evaluation of drivers. Exponential random graph models were adjusted for each one of those 3 subnetworks based on transported animal, and they were validated by cross-validation comparing simulated network to observed network. Here you can see on the left the second semester of 2019. Those data were used to calibrate the exponential random graph models, and the second observed network are the one observed during another semester. I choose randomly the first semester of 2018. So we also validated the exponential random graph model using goodness of fit approach. We compared network statistics for observed and simulated networks. The box plot that you can see here, so this one is for reproduction for the south movements. They represent the network statistic, the box plot of the simulated network, and the colored line graphs. I hope you can see that all 3 models were quite well fitted. And at this stage of the study, we had almost everything we need to simulate the metapopulation dynamics within and between farms. As input, therefore, we used a list of detailed farms, including structure, batch rearing system, and contact probability. So we used, we now had to use an incomplete sampling plan to estimate the final parameters that were the maximal number of potential destinations for each type of transported animals to be closer from the observed data. And now our model was able to simulate national metapopulation dynamics in a discrete time, so daily time step, at a pen level, including within and between farms dynamic. So once again, we used the cross-validation approach to validate our models through the visual comparison of maps and with the goodness of fit approach. Now that we know how animals are distributed in the farms at national scale over time and how they move between them, we want to know about the epidemiological state. So still working at pen scale, we used a compartmental model, including the environmental variable, defining the viral load in the pen environment, and 5 epidemiological states where animals are distributed. So the animals with maternal antibodies, the susceptibles, exposed, infected, and recovered ones. The transition between the different epidemiological states were mainly driven by 3 transmission rates: the direct transmission, the within pen environmental transmission, and the between pen environmental transmission. And stochastic disease spread was simulated based on a Gillespie algorithm using a Siemens package that I think many of you know. So we have now a very flexible epidemiological model allowing to simulate hepatitis E spread in a complex metapopulation divided into structured farm with different epidemiological variables and the output of the demographic model. So yeah, to face memory challenges, just because as you can imagine, if we are at the pen scale and at the national level, we have a lot of nodes. So the model only record in output the daily epidemiological state of animals sent to slaughter, which was actually our goal from the beginning. So as an example of output, this box plot illustrates the average prevalence among animals received in all slaughterhouses of the country over 5 years. Colors of box plot emphasize the stability of the network despite stochasticity, and the minor effect on the epidemiological output. Nevertheless, left and right box plot, so this one is really low and this one quite higher, are the prevalence resulting from different set of epidemiological parameters. On the left, we use general epidemiological rates estimated for HIV. These very low prevalences are realistic in regards to field observation at slaughter age. And on the right side, we used epidemiological rates estimated in farms where there are animals co-infected with immunomodulating viruses. So we see a significant effect on those parameters on the output, and in the future we'll do a better sensitivity analysis to see the effect of the different parameters. So to conclude, we designed a global approach with a highly flexible tool to simulate population dynamics and disease spread. The ERGM, so exponential random graph models, appear to be appropriate tools to analyze farms' interactions. And now with the fitted model, we are able to generate between farm contact from only a list of structured farm without updating the movements, which are a lot of data to collect. And therefore, additionally to the non-negligible improvement of predictive capacities of our model, it will contribute to ease the future initialization of the model. Moreover, the flexibility from the pen to the farm level allow us to test a large panel of measures on various range of farmers' community. And in the future, in the BioPG project, the epidemiological output should be used to feed the quantitative microbiological risk assessment model to evaluate the risk of human exposure to HIV through swine production. Thank you very much. If you have any question.
Thank you for this very interesting talk, and yeah, the model and the method seems very nice. So are there some question? Or we'll proceed like usual. I will start and then this may come other questions. So yeah, it's quite impressive because you're estimating the. I mean, you have a model for animal movements, and then before which is nested in the epidemiological model. So I was just one question for to be sure that I understood. So which is the temporal aggregation window for the prediction for the model of animal movements? At which temporal scale are you able to correctly predict the movements?
Actually, the ERGM was calibrated using a semester.
Okay.
But then so from the ERGM, we have a list of probabilities of contact between farms, and then with the demographic model that we developed with Stefan, we have movement aggregated at daily time. So each day we have movement from between farms based on those probabilities.
Okay, but the validation was done at the for 6 month time windows.
Yes, just the map actually. Yeah, it's aggregated. Yeah, this one you mean?
Yeah, or even the graph, the goodness of fit graphs, or the
those are yes, also
the cross validation. Everything was for 6 months.
Yeah, yeah, because we saw on the I was here. I went quite fast, but we see that the variation between semesters are quite small. So what the semester are the box plot in the middle for the where there are from first semester of 2017 to second semester of 2020. So to 8 semesters.
Okay.
The values of the statistical the network statistics that were calculated were quite similar, and to observe the production cycle, like all the growth chain and several destination for between farm movements, we choose to use this 6 months.
Okay, so period. The choice was the smallest, but stable period.
Smallest, stable, but not the smallest possible, because for example the months say is also quite stable, but we couldn't see the multiple destination because of the duration of growth. For example, if you take one farm, for example 1 farmer, the time between two export of animals, of piglets, will be longer. Two If I take only 1 month, I will maybe have the chance to see one export, but not 2 or 3. It's just because we want probabilities of contact between farms. We wanted to see multiple exports.
Okay, and on the graphs that you showed, I mean the maps of observed and predicted networks.
Yeah.
I was not these ones. We have some 3 columns. You have another slide.
So that are the
You have
yeah,
this one.
yeah.
I was no, but like a visual feeling. It was like that predicting. So simulated networks were more dense than observed ones.
Yeah, actually, that's true, but those one are not temporal. It's just exponential random graph model. So it's a randomly simulated network based on only the probabilities of links appearing in the network. So actually, as you can see for the sows, it's better than for piglets, even better, which is better than for growing pigs. And it's also what we see, but you can see here, but it's yeah, it's denser, and we wanted to just have the probabilities of contact, and then the creation of links will be managed by the whole functioning of the demographical model based on real needs to export animals or to receive
You
to
have only
import
the
out.
backbone in some certain sense, and
Yes, exactly.
then
This is really just to have the probabilities of contact. For example, if I have new farms now and I inject them in those models, I will be able to say, okay, because you are a farmer, because you belong to this specific company, because you are a small producer, you will have more chance to send your animals to those farms rather than this one. So for simulation.
okay. And I don't remember in the pig movement network. Do you have hubs, or is a more homogeneous network?
Do I
Do you
have what? Sorry.
hubs? So
Um,
nodes that are
yeah,
very
yeah. Actually, there is a huge one in Brittany, of course, and this the first model that was developed by Morgan Saline, Mathieu Andro, and Stéphane and Nicolas was only based on this huge community.
yeah.
But
There is a community, but are there hubs? Because no, I was just it was to discuss, because I in networks with hubs, as we can see for cattle movement, there is an additional difficulty to build a predictive models, because the hubs they have particular behavior. So that's why I was asking. I see that there is a community, but that's one thing. But hubs are like
yeah,
no unique nodes that have huge number of connections.
yeah. I cannot say for sure. I don't remember, but
Okay, no, it's not.
the degrees. You mean nodes with I between us or stuff like that, or
Or not with high degree nodes
high
with very
degree?
high degree.
For example, the degrees were quite homogeneous, actually.
Yeah. So it's not the same topology that for cattle movements as far
But
as I see here, but maybe
there is also the we did a first approach by dividing. I don't know here. You know, maybe notice that those farms are in pink and those one in green. It's because those are the breeding part of the production. So those farms are have more higher out degrees.
Okay.
than for those farms, but it's what's also taken into account because in the exponential random graph models, so we used, where is this? Okay, so we used these different characteristics per nodes and per edges, but per node, each time, each characteristic is related to a statistical parameter, which is called term in ERGM. So for example, for the type, we choose the I factor. So
Okay.
it's the input in the, it's related to a degree and its degree.
Okay, so
And we
sorry,
also
I
choose
took all the time for discussion. So I'm very interested in your work. That's why I asked many questions, but I didn't let time for the others to ask questions. But anyway, so I think we should stop here just to not to be late for the next
yeah,
speaker.
thank you.
Thank you
Everyone.
again.